That's what we're going to start Pascal's principle. Anybody want to describe what happened?
I'll tell you.
Elizabeth?
Okay, so me and Sheree.
Let's listen, please.
Well, our first video, she was the one who really pushed the egg, and so she put the egg in her.
Yep.
Yeah, and she said, "I'm gonna break it," and she did. Like it broke. And then I tried it, and I tried like real hard, and it didn't work.
It did break. Did you try it again afterward? And how did it work the second time?
It didn't break the second time. Because it was right with the angle I was holding at the final.
Or maybe she's
Good point to notice right away. That's the first. So Sharice tried it once, it cracked. Then Elizabeth tried it, wouldn't crack, and Sharice tried another one, it wouldn't crack either. Give me some other. We'll talk about why didn't. We'll take ideas. But what else happened? We'll tell the class in case they haven't.
Basically, what happened was that yes, I sat on the edge before it crashed. No. What happened was that I was actually over at my house. What happened was that I was trying to crush the egg. It came straight from the refrigerator.
By the way, that's called a raw egg. You in your video said, this is a hard-boiled egg.
Yeah,
I said, not to use hard-boiled egg.
I didn't know what it was.
It's called a raw egg.
I don't know how it's not
Hard-boiled is you put in water, you boil it.
Whatever. Anyways, it's an egg regardless. So I tried crushing it, and it couldn't really work. Then after that, I couldn't really crush it, so I actually kind of wanted to do it herself. So I was like, all right, go ahead. So she tried, and she couldn't really do it either. So she uses both hands and uses her entire arm, and like it breaks, but like it flies all into her face. All the egg.
And there's a reason why it broke so bad. I'll explain that also. Any other? You squeezed it, it didn't break? And did you eventually able to break, or you just kept trying to would break?
No, I put it back.
Good call. Say it again. All right. So there's a few things going on here. First of all, the whole theory came about from Pascal. In the 1600s, he was looking at a barrel, like an oak barrel, that he used to put like meat in, where there would be alcohol in, oak barrels. And he noticed that if there was too much pressure, if there was too much fluid trying to go into the barrel, it would eventually like start to leak. And the barrel had some problems with leaking. And what he noticed was that it leaked. It started leaking everywhere at the same rate, which to him was very confusing. He said like, well, why isn't the bottom leaking faster than the top? Well, you think more would be leaking at the bottom than the top? But the idea is that the pressure on the barrel inner wall, for example for the egg, the pressure, if it's consistent around the whole side, it will be like kind of counteracted by the pressure of the fluid. So if you take an egg in your hand and you try to crush it, and you try to crush it evenly, that was the whole key, evenly. If you do it evenly, so you lay it in your hand so that it's sitting like perfectly in your fingers, and you cuff it the whole thing and then try to crush it. If you try to crush like a corner of it, it'll crack. Like a normal egg will crack if you impact the corner of it, right? Karen's video, I was laughing at because she thought I said to try and crack it and then crack it again in her hand. So she started by like cracking the edge of it and then went to crack it. And it turned out though, it wouldn't break even after she put the little crack in the corner, which in itself was amazing. I didn't think that would happen at all. So she tried to crack the corner first. Somebody in our class. So the idea though,
sitting in the front.
The idea was this. And Sharice, you mentioned it a minute ago. When Sharice cracked it the first time, she said, I might have put more pressure on one spot or too much force on one location. And the idea is that if you displace your force over the whole area, your pressure goes down. It's like the example the other day. Very little pressure is on my legs, but the minute I go to 1 foot, I have double the pressure now because I have half the area. Now if I try to stand up, I have even more pressure because I have less area. So if you concentrate all your force on one little spot on the egg, it's a lot of pressure. That's what causes the crack. But if you spread the force out from your hand on the whole egg, it itself, the fluid within it, reacts with like a normal force acting back outward. Again, the whole idea only works for a closed volume or a closed surface. So the other day we did the example, okay, with a car here, and then a force pushing down on like a piston, and it would move the fluid around, lift the car up. The Yeah, there we go.
The
The example of the car was an example of Bernoulli's principle, another one, of Pascal's principle, because of the fact that this fluid, it can't just start flowing out of the container. Okay, nothing can just start flowing out of here. It's closed. It's a closed container here. So the fluid that's within it will just transfer pressure along from side to side, just like the egg. The egg got all the fluid inside of it, so when you try to squeeze it, all the fluid reacts backward in equal and opposite directions across the whole surface, or across the entire inner surface, you could say. That's why it doesn't cause itself to crack. You still make egg videos? It was supposed to be before today, remember? Because it was before Pascal's. Sure, I gave everybody that did it already 2 bonus points. If you do it now, I'll give you 1. Still get something. Okay.
So what about that speaker?
Now you can do whatever, yeah. That was fine. And Adolfo, I think, said he did that already.
You haven't watched the video.
I haven't seen the video
Oh my
yet.
god.
Why, it's funny?
Yeah.
6 minutes of Adolfo narrating? Oh, no. Anyway, the idea of Pascal's principle is one of our two major fundamental theorems we're going to use for fluids. The other guy that I keep mentioning is Bernoulli. Okay, we'll talk about him eventually. What we're going to do today is the following now. We're going to start to talk about pressure, again still, but underwater now. So last class, we talked about pressure as if I was standing on something, or we talked about pressure like we were punching an object, but now we're going to talk about pressure underwater. Not just pressure from the car, hydraulic lift that's going to move the car up and down, but what happens to like a submarine. How can we know a submarine won't just implode from all the pressure? Why won't it just collapse on itself?
Now, we don't have no more tests this quarter, do we?
Probably not. No. Friday's the quarter, so no, we don't. Yeah. Next quarter we'll have one in the beginning.
Everybody's sneaking in those tests.
We're gonna do a lab tomorrow, just for a heads up. Okay, so you guys know. Yeah, I'm gonna make it. Well, I'm gonna think about it. Let me think about it tonight, and I'll tell you.
Because
tomorrow.
everybody's sneaking in a test for some reason.
No, we don't want grades. I'm fine with grades. If we get the lab done, we might push it in the next quarter though, just because it's a longer lab, much longer.
Are we gonna crack the egg?
We're gonna do something with an egg later in the year, actually. It's something really cool.
When I looked at the egg, I don't think it fully cracked. Like, you know how there's different layers
Yes,
to the egg? I think it still had that, like, thin layer on it.
and that's the membrane that actually gives it the structural support.
So I guess that's what.
Yeah, there's like 3 or 4 cell membranes that are outside of an egg. Yeah, one of them works as like against osmosis, so fluid can't flow in and out. One of them keeps it in structural support. So depending on which membrane you're looking at, they have different functions.
Oh, yeah. But I think my experiment.
Scrambled egg is just a cooked feed.
We're continuing pressure. Continuing pressure below water. No, that was it. Pascal's principle is what we just said. If you want an actual word definition, look here. Okay, it's on page 280.
It's delicious.
All right, so you have to use your imagination here.
Okay.
Imagine like we've been talking about a. Listen, please, come on. Imagine if you have a box of some sort, a 3-dimensional box, a crate, that gets dropped into the water, or like something like, imagine a dice. Okay, so you're rolling a dice, but you take a little fish tank and you drop the dice to the bottom of the fish tank. So the dice's shape is a simple rectangular solid. It happens to be a cube. Okay, we're going to talk about pressure below water. Okay, guys, Bernoulli's principle is just the fact that the pressure inside of a container just exerts itself in all directions. That's why I said it. I said it several times verbally. Okay, if you want to see the exact words, on page 280. Okay, page 280 if you want to see the wording.
Pascal or the other two?
Bernoulli?
Yeah.
Bernoulli's next chapter. I mentioned his name before, but I said we're going to wait to talk about him. I said it by accident. I said we're talking about pressure below water. Yeah. Bernoulli has to do with flowing water. Or flowing.
Before you get a little off topic, what about the hexane? Miss Stacy also commented saying something about Pascal.
Ah, good. I didn't see that.
So like she was mentioning how that actually correlated to the eggs. So.
I also mentioned that in mine too.
Yeah, but I didn't really read it.
I can read the comment I wrote. It also says, look at Pascal's principles. I wrote a lot to explain to you.
I'm thankful for that.
All right, so
Is
this crate is sitting
that like
Okay.
an ocean or?
under the water in the ocean. Now, the way we can visualize is the following. If I'm standing on a certain area, all of my force is concentrated on that area.
Right.
So the area around my foot, it feels the force a little bit because it feels the reverberation from it or the result of it. But the force I'm applying, the pressure here, Terrence, come on, guys, this way. The force and the pressure I'm applying is only on the contact area between my foot and the ground. So the pressure that this surface right here feels, this surface right there, it feels pressure from the water that is above it. So we talked about this last class. Imagine a channel of water. Imagine a channel of water extending upward. And that channel of water is also a rectangular prism. That's what's applying a force down on this object right now. That water. It's got other water from the sides, and that's different. But we're talking about on the top. There's a certain amount of water pushing down on that actual surface.
So you said there's water coming on the sides, but so is there pressure on the sides?
There's pressure on all sides, absolutely. But we're going to talk right now to simplify to say what happens to the pressure at a certain distance. We're going to make believe there is no real width of this object, and we'll talk about how we can do that in a minute.
Yeah, I was just gonna ask, the only reason that is there only pressure on the sides because of the current of the water, or?
No, I hear you saying, you mean because the water's flowing back and forth this way also?
Yeah.
There's pressure just from the water around it, yep.
Okay.
What we're going to do now, though, guys, is I'm going to show you a way to derive or come up with the idea where we can say that the pressure is only a function of its depth alone. We could ignore the shape, and we're going to find out ways to do that in a minute. Okay, and it's a little bit weird to think about, it really is, because we know that different shapes, will have different pressures. But we're going to come up with a way to ignore the shape. We're going to show how the areas kind of drop off, and we'll talk about that now. So let's start. And this is going to be a very quick derivation. It's not going to be a long one. We're going to look at like 5 parts, but when I say something, you might want to write down why I made the correction or why I made the change. And if you want to look in your book, it's simple. It's on page 282. It's the same thing that I'm going to go through here. I'm just going to try and go in the same order that they go. So we start with pressure equals force over area. Okay, that's from last class. We already talked about this. We talked about how P in the past had been power, but now in this chapter with fluids, we're talking about pressure. So pressure is force over area. Now, the force, let's think about this for a second. The area that's being acted upon is this square area right here, assuming it's a cube, of course. But this, in this case, we could say rectangular. It doesn't matter. But this red boxed-in area, that's the area we're looking at. That's the A value right here. Okay, that's the A. Now, the force that's going on here, again, is the water on top of it. It's the water on top of it. So I want to know the mass of this water, okay, the mass of the water times G. So I can start by replacing with this with mass of the fluid times G over the area still. Okay? The pressure that you're always feeling the result is the result of the normal force. Absolutely, good mark. Good, not mark as a nap, but good note, sorry. Use the wrong word. So the pressure that you're feeling is the normal force. The normal force is a result of the weight of the water. Okay, MF is the mass of the fluid. Now, we talked about this last section. This is where you have to start going back and thinking. We also said that M, what could M be represented as?
Mass?
What could mass always be represented as now that we know about fluids? What was another way to represent M?
Force.
Volume? Density?
You're in little parts, but not the right thing from anybody.
What's better? Isn't that
Oh,
P?
apparently.
What can I, my question, guys, is this: what variables can I replace mass with now that we know?
W.
We know this, right?
W.
Density equals mass over volume. So solve for mass. Come on.
P over M over density.
Volume times rho. Again, we want to get M. I'm asking you, what can mass be represented by? Think back to what we know. Take the V, move it on up. V times rho. So we write rho of the fluid, V of the fluid, G over the area. So again, what have I done now? I've replaced the mass, this portion right here, with rho V. Okay, with rho V. Rho is the density, V is the volume. Okay, the volume of the fluid. See the fluid on top here? See all that fluid up there? That's the volume we're looking at. This blue channel, not the object itself. Notice I put the subscript with an F. It's very important that you note that. Now, here's what I want you to notice next. This is where we talked about extrusion. Remember we talked about extrusion? And how it's like taking a cross-sectional area and pulling it through an object, and you get that shape. So for example here, if I look at this shape of this chamber, or this channel, this is a rectangle times some height. And I know that the volume of this chamber, the volume is always length, which is this way, times width, which is this way, times the height. But the length times the width is really the area of the base. That's that red area right there, times the height. Again, remember back from geometry, area of the base is really L times W. So my area of this chamber right here that I'm pointing to is LWH, always. But instead of putting LW, I'm going to put the area of this base. Because the area of this base here is the same as this area down here. Notice this area down here that we started with in the very beginning was defined as the area of the top of the box. Well, that's the same as L times W. So instead of writing LWH here for the volume, because then I'll just cancel LW with A, I'm going to write LW as just A. So I'm going to write it like this. Rho F, area times the height times G all over A. Again, what am I doing right now? I'm replacing the VF, the volume of the fluid, with the area of its base times the height. That's the whole idea of the process of extrusion. If you know the area of a base and you multiply it by the height, you get the volume of the resulting shape. So here, this is LWH really, but LW is area, so I'm putting area there so I can then cancel. What am I left with? The density of the fluid, the height or the depth really down below, times G.
Like rho, are you saying that like the pressure that the top face of the cube is feeling is the same as like the pressure that the highest point on a sphere feels?
Absolutely, at the same depth. Very good. So what he's doing is he's taking a two-dimensional plane and using a derivative or using an idea of a limit, and you think about it to a point. That's what you're doing right now. So imagine you had a sphere. That is what you're doing though. You have a sphere. The pressure at this point on the sphere is the exact same pressure as this point right here. Because clearly, take a look at what the pressure is a result of. Pressure underwater is a result of the density, which doesn't change, the depth, or H is the depth. Well, these are at the same depth, aren't they? They have the same H value, and they have the same G value. So we can see that the shape of the object really has no actual effect on it now, which is an amazing result to come up with.
What I mean, wouldn't that be like, instead of having that single point on the sphere, wouldn't you have multiple of those on the face of the...
Every single infinitesimally small point on this box has the same amount of pressure that this one point does right there. It doesn't matter though, because pressure is per unit area. So it doesn't make a difference. It's a rate of change, or a gradient you would call it. Because these have the same pressures, it's not like all those pressures are adding up. That whole face experiences the same pressure as this. It's no different. All it is about whether or not the object can withstand it. So if this object is made of metal, and this is made of metal, they'll both be probably good to go. But if this one was made of, like, I don't know, foam, well, that would rise, actually. Let's say it was made of plastic, and this was made of metal. This one might collapse because it's structural limitation. Okay, it has a yield point, and we're going to talk, if you talk later in material science about a structure, it starts to, like, break, it starts to stretch, and then it will break, and it will deform. This is called the yield point. But we'll talk more about that later in the year. But plastic's yield point is much less than metals. It's ductility. It will start to break first. So this one might break based on its material. But based on the shape alone, it makes no difference. Because clearly, now pressure, we start with here and we ended up all the way over here. Pressure is a function of the density, the depth, and the gravitational constant. This is the same. We're not going to change that. We're going to assume 9.81 for all things, even though it does kind of change with depth. The H is the depth below water. So please remember now, H is not height. I mean, we call it height, but it's the height of the water channel. So if you want to write down next to H, if you want to write down depth, that might be useful to write that, okay, for H. Rho F is the density of whatever the fluid is. You know that already. Okay, in this case, salt water. that would be 102.5. Okay, if it was fresh, 1,000. And then ice, anybody remember ice?
971.
Very good, 971. So our conclusion here is the following. We showed the derivation, here's the conclusion.
I zoned out for like 20 minutes.
This is how you're going to see the formula over and over again. Rho GH. Remember, please, rho is rho of the fluid. So if you want to add it, I would add that there. But they don't usually give that there.
I don't like fluid.
Okay, density is the density of the fluid because this is fluid pressure. So it's the only thing you're going to matter. All right. Now there's a term for this. There's a term for this. We call it gauge pressure. So please write this down. G-A-U-G-E, pressure. Okay, that's what this is called. If you are underwater and you have a certain amount of pressure acting on you from the water above you, we call it the gauge pressure. Because you can measure this with a gauge. There's actually a gauge used to do this. And I'm not sure if that's the etymology, but that's how I remember it. Doesn't matter how you remember it, just think about it that way. It's the pressure from the fluid. Right? Can you measure the pressure on your tires? Yeah. You put your actual, what do you put up to it? What is the word for pressure, Peter? Starts with a B?
Barometer.
What is it? Barometer, very good, barometer. You said thermometer, you didn't say barometer. You said thermometer.
It's the same thing.
That was good. Barometer. So, you can measure the pressure of your tires. Put the barometer up to it, it pops out as far as it goes, or you have a little digital scale, whichever one you like. I would recommend, who has a car here? Anybody have a car? I didn't have a car until I was 22. If you don't already, listen, if you don't already, you should have two things in your car at all times. You should always have jumper cables. Okay? You should always have jumper cables, seriously. You should always have a way to fix a flat. Whether it's a spare tire, whether it's something that you can actually enclose a flat with. You should also, I keep this in my car, so I do it all. You can buy them, and they're pretty cheap actually. They're like 10 or 15 bucks at Target. There's these little things, they're air compressors. You plug them into your actual electric jack in your car, or you would call it like they used to be called the cigarette lighters. They don't have them anymore. They're just the 9 volt or the actual things there. Look, new cars don't put them in there anymore.
It's just a plastic. It's just a plastic.
It's just a cover on there. It's actually a lot safer, guys. It's a lot safer. It's a lot safer. They don't do it for no reason. Anyways, that's not the point. The point is this. You get these things like air compressors. You plug them into your actual electric jack, turn it on, and you can fill the tires to your car at any point in time. You don't ever have to stop to get air in your car. It's really cheap now, and they're very widely used. And it's a long cord. It's a compressor that generates pressure based on an electrical circuit that it gets energy from the car. It generates this pressure. You attach it to your tire, and you can fill up the air in your tires. So if you ever get like low on air, it's the winter, and air, the temperature goes down, the volume goes down. You'll start to see a flat in the winter. If you want to fix it yourself, you can actually just attach this thing and then fill up the air. The one I have, it also has a little barometer on it. And the reason it has that on it is because if you fill up the tire too much, it can pop. Now, it's not really...
That's what you need a penny for. That's like you put a penny to grip the tire, and if you can fully see leaking ahead, you have enough pressure in your tire.
Is that right? Now what happens if your treads run down? Then how do you know? What do you mean? You saying between the treads?
Yeah, like... What you call that? If that's what you call on the tire, you know how you got the little
ridges,
lines on it.
Yes.
You stick the penny through it. And if you can't, it's opposite, I think. If you can't see his whole head, it's not enough pressure. But if you can, like to his neck, so I don't know. I'm up here.
The rule, you're probably right. Actually, it probably works really well too. I never heard of that. I gotta look it up. So you just take a penny and measure to see how much you can see.
Do a penny, yeah.
These are good tricks to know, guys. These are always good, because what if you don't have a barometer, right? And you want to figure it out. These are good things to always know. So he's saying,
I'll just use the formula.
I don't know if you can tell while you're on the road with nothing else.
In the middle of I-95.
You know how your tires have like treads to grip the road on them with these little ridges? Terrence is saying if you put the penny in, if the ridge is out far enough, it means there's enough pressure probably because it expands, right? So if you see a certain amount, you know to stop.
I did it so long.
Can you ask her? Let me know, yeah, that'd be good to know. Anyway, back to the idea, guys. The idea is this. This is gauge pressure. It's a pressure that you're going to measure. So when we're looking underwater, it's the pressure from the fluid above it. Now, think back to about, I don't know, maybe a week ago. We were talking, and I said one thing. I said, remember you could say to your teacher, I'm under a lot of stress? Because technically the atmosphere is pushing down on you. Okay? We have to consider that now. We have to consider that as well. And here's what we're going to do. We're going to look at an example. So let's start with an example. We're underwater. We have an object, okay, sitting underwater. Let's say it's suspended for some reason. Maybe there's like, I don't know, maybe there's a column over here and here, and it's linked together with a chain. So there's this object suspended underwater, okay? So they do these things. You ever see like in the Caribbeans where they go under and you go on this cage and sharks come up to the cage and like you could swim with the sharks? That's the kind of stuff. Well, they have to have you somehow secured so that it's not going to, you're not going to go floating away. It's an example of that. It's an example where you'd see it.
Not really swimming with sharks.
I know that. I understand.
I'm just spending in water while I'm trying to eat you.
It's like freezing.
You should just swim. Yeah. That's pretty much what it is. On the commercials, they should say that. You're going to swim and suspended in water, shark's going to try and eat you. So, so you heard that, right?
You heard it too, right?
Yeah, that was a bird. I thought it was something like last week.
Yeah, I heard it too.
I don't remember it
I'm still young about that. I was the final four. I could have won. It was me, Chris, Hey, I remember the metro. I was still.
Oh my god, I'm so happy.
So, we've got this box here suspended in the water. The question is, where is the pressure higher, on the top or on the bottom? Okay?
It's actually on the.
So let's do something simple first. Before we actually go through this, let's take a poll, get an idea of what people think. If you don't know, you don't have to vote, but I encourage you to vote. So you're going to get three options. You're going to have three options. First, the answer is on top, the answer on the bottom, or neither. So it's the same. Again, your options are more pressure on top of the box, more pressure on the bottom of the box, or the same on the top of the box. So I'm talking about the sidewalls right now. Top and bottom only. Okay? Hands for more pressure on the top.
Unless your dagger is right.
Okay, 3, 4. Hands for more, so top is 3. Hands for bottom, more pressure on the bottom.
I don't know. I want to say.
5.
I just saw a dark figure and just open. And then around open.
It walks slow.
That kid right there. You reacted too slow.
I know, right? All 30 of you. We got 5 for bottom. Now, neither. Hands for neither. So, or same for both. Same for both. You moved all 3. So, Edgar voted for all 3, so his vote for us doesn't count. You change your mind every time.
Y'all on top and bottom.
You meant to just
All right, so that's what you meant? The bottom, right? Or same. Okay, so, simple way to look at it, guys. A minute ago we said, pressure equals rho GH. If I am on top of the box, or on the bottom of the box, the density of the fluid is the same as water. It's salt water. Agreed? G is the same, we're saying. Again, we're saying that G is the same. What's different though? The depth, or H. When it's deeper, isn't H more? So on the bottom of the box, there's more pressure. That's all you got to look at is your mathematical verification. Again, this has no effect on the problem because the density is the same on top and bottom. This has no effect, but the depth under the bottom here has more height or more depth. That's all you have to think about. It sounds weird.
Does it matter?
It doesn't make any difference. Use, three-dimensional Euclidean geometry. There's no argument whatsoever. Of course I did. In the beginning I said this was the top and that was the bottom.
I don't see how it's difficult because like you told it that all of the gravity's not gonna have any type of control underwater.
Julian, without the formula, right? And you just had a box underwater. Would you really be able to figure out if there's more pressure on top or bottom?
Yeah, because you told us that there's more pressure underwater.
No, not on top. I mean on the top. This is all underwater, Julian. The whole thing is underwater. This is just a chain, guys. These are chains linking this together. These are chains. This is the water level up here. So either way, it's underwater. The top surface is underwater, and the bottom is underwater. It was which is more pressure underwater than. If it was half above and half below, then sure, yeah. I got you. All right. So now, the general conclusion anybody can write down if you want to is as you go deeper, there's more pressure. It's very, very logical. Again, they are directly related. As you go deeper in the water, there's more pressure. And test it out yourself. Go to the bottom of the shallow end, you don't feel much pressure. Go to the bottom of the deep end, you feel the pressure in your ears. Okay? Yeah. Even before you get down there, true. All right, next thing we need to talk about. An object underwater still. All right. We talked about the idea of the column of water. Okay, the column of water weighing down on this object, and how the column of water is what creates the pressure. Now, we really have to extend that further, because if you have the water, imagine you're standing in front of a pond, and you see the water in front of you. All that column you see on top of maybe an object under the water, a shoe, or a rock, or something in the water, that column you see extends further out of the water. Because once you go out of the water, you're still in this fluid that's around us that we call a gas, but it is a fluid. So really, not only is there pressure from the water, but there's also what we call atmospheric pressure, which is the pressure from the gas that occurs in the atmosphere.
But it's so small.
Let me explain. So again, I talked to you last week about the idea that you always have stress on you. You always feel like there's stress on you, because really there is. The atmosphere has gas above you. It's a fluid. It's weighing down on your body. Now, if you look directly at this channel that extends infinitely toward the end of, well, not infinitely, but what we consider infinitely, but when it gets to the end of the atmosphere, it's pretty much done. Once you're outside the atmosphere, there's no pressure weighing down on the earth. The atmosphere is like your eggshell. Think of the atmosphere, the outer atmosphere, as the eggshell. Once you're outside the eggshell, the pressure on the outside is not affecting that egg. Okay, this case, we're looking at this column that's above the water that extends to the top atmosphere level. And there's a certain amount of pressure that exudes on any object. And it's the same no matter what. Okay, it's the same no matter what.
So how
and that's what we're going to show right now. If you want to figure out the actual pressure, okay, which we call the absolute.
Which is outside?
The absolute pressure, which is the pressure no matter what, underwater, above water, wherever you are. Here's what you do. You take what's called the standard pressure or atmospheric pressure, and you add to that the rho GH, which we talked about a minute ago, and we called that the gauge pressure.
Is Po density or is it Po
It's rho. Not
Oh,
po.
like P-O.
I thought you were calling this symbol po. In high school, I used to call theta, like feta cheese.
You know, hey, you
I thought it was
Like
spelled
feta?
F-E-T-A, not
Feta?
T-H. Because my teacher had a list, and she would say theta. And I'm like, theta? You saying theta? So all year I wrote down theta until the final exam. I saw the word theta. I was like, what in God's name is this theta thing? She keeps talking about. So I asked her on the test, you know, Miss Carpenter, what is theta?
Miss Carpenter.
I remember it, ninth grade teacher. I go, what is this theta value you wrote down? She goes, Mark, what are you talking about? I'm like, what's theta? She goes, you're serious, Mark? You don't understand this. I'm like, I mean, I know what theta is. Is that what you mean? She's like, theta cheese? And like we started both laughing in the middle of the final. All year I thought it was theta. Anyway, sorry. Po or rho naught. We call it.
What is that called?
This is the pressure, okay? And whenever you put a zero, it means like the pressure to start, your initial pressure, no matter what. So even if I'm above the water, this is the pressure that I feel in my body right now. Okay, this is the number of the pressure or the amount of pressure that I feel on my body from the atmosphere. And if I'm underwater, I have to not only take that pressure, but also add the pressure that is the gauge pressure from being underwater. So this is the atmospheric
AKA initial pressure.
atmospheric pressure. How else would you say?
No, I said it like a.
Okay, atmospheric, I don't know. That's a RIC at the end, RIC. Okay. So atmospheric pressure. Now, the idea is this. If you've got an object, you can figure out the pressure from the water, but this is so significant, it is significant. Not insignificant, but it is very significant, that we cannot just ignore it anymore. Okay? So if you want the pressure on a submarine, you have to take the pressure of the actual atmosphere plus the water pressure and combine them to get what we call the absolute pressure. Okay? You need to add both. The cool part is this, guys. This number is the same no matter what. It's a constant like G. So you don't have to worry about rho naught or rho naught, P naught. You don't have to worry about P naught here. Naught just means this little symbol, by the way. N-A-U-G-H-T. Okay? Naught. Let's look at an example to make this easy as anything. We've got any object. I'm not even going to draw it. I'm just going to write a word problem. Think about this logically, by the way, when we do these problems. 200 meters, that's approximately 600 feet. It's not really, but just triple the number at least. Think about how far down you are. We're talking like a little over 1/10 of a mile down below sea. Let's write down salt if it's the ocean. Whoever's got them can put them away, please. No chips, you know that.
Holy crap. I was like,
Got you.
No, stupid.
You didn't hear that, Mr. Hoffman?
Switch the U and the A in gauge.
Thank you.
Talk about that last year.
You're talking about what?
Hey, Cheryl, what's the $28 question?
Teach me how to do You probably talked about it if you looked at like, if you looked at STP, standard temperature and pressure in chemistry. You use this a lot. It's atmospheric pressure. All right. Now, before we get started with this problem, I need to take a minute to explain units here.
Oh, yeah.
First, KPA. PA is the unit for. Ready? PA is the unit for a Pascal. Pascal. The K is kilo. Very good. Just like kilometer, kilogram. Okay. KLO is just a prefix. So the K is the prefix. PA is a Pascal. A Pascal was not defined until the late 60s, the 1960s. Even though Pascal was around the 1600s. So for a long time, they just looked at the actual units. Remember, the value for pressure is the force over the area. Tell me, everybody, what's force measured in? Newtons. And what's area measured in? Feet. Something squared, and we in this case we use meters. So pressure, its units are really newtons per meter squared. Again, because it's a force over an area. But a newton per meter squared was defined as a Pascal in the 60s. So when you see a Pascal like that, just think of a newton per meter squared. Okay? Again, newton per meter squared. So in this case, we're looking at not 101 pascals, but this is really like 101,000 pascals. Kilopascals. Kilo means times 10 to the third. Remember, this is 1,000. Just like a kilometer is 1,000 meters. A kilogram is 1,000 grams. This is 1,000 pascals, but it's 100 already. So this number is 101,000 pascals. It's a very large number. So when we use our calculations the next minute, we want to convert to kilopascals. It's our standard units we're going to use. So let's go ahead. Two things we need. First, we need the gauge pressure. Second, we need the absolute pressure. Those two things. Christian, how do I get the gauge pressure?
From the
Good. There's my gauge pressure from earlier. Remember, your gauge pressure will always be rho GH. Rho GH. Rho for water under salt though. Salt water. What do we say? What is it? Very good. 1025. Now, to be consistent, I'm going to put units for now, so we can see here what's going on. How far below water did I say?
I don't know.
200. You got to write it down. Meters. Now, with that said, we want to go ahead and take a look and see if our units actually work out here. For this problem, we've got 1025 kg per meter cubed. Where do these units come from?
They came from
Why is it kg per meter cubed again?
Bro, isn't it mass over volume?
Mass over volume. Remember, density is really mass in kilograms over volume in cubic meters. Gravitational constant is always meters per second squared. Our depth is simply in meters. Okay, our depth is simply in meters. So for this kind of a problem, we want to go ahead and look, multiply. Our units will work. They're a little messy. Once we do this problem once, I suggest that you just drop your units and write your answer with pascals as your answer. Because they will come out to be pascals, but it's a little bit messy. As long as they're all standard like they are right now, you'll get pascals. But I'll prove it to you why. So I want you guys to multiply the numbers. I'll leave a blank for that. I'm going to show the units over here.
kg times S.
That's what the units look like when I line up my units here. Again, this is my gauge pressure. And what I see here is this.
M squared.
I get kg over, be careful though, cancel, cancel, cancel these two, over ms squared. And it looks like at first that's not a Pascal. But if you look carefully, a Pascal is a Newton per meter squared. We said a minute ago it's force over area. But what's a Newton? A Newton is a kg m over s times 1 over m squared. And what you look at here is this. kg, kg. M, this m cancels one of these m's. That's gone. I'm left with m, I'm left with m. Whoops, n squared. And s squared ends up with your s squared here. Okay, this is what a Newton always is. Remember that. And this is 1 over m squared.
Me, right?
Yep.
But I thought you said a Pascal was kg over meter squared, right?
A Pascal was a Newton over meter squared. It's a force over a unit area. That's a Pascal. This is the units we end up getting, and this is what units of Pascal should be. If I break up a Newton into this portion of a Newton, which is what a Newton is, and then I put the m squared as 1 over m squared here, I see that these are identical actually. So whatever I get from this, even though it doesn't look like a Pascal, I'm trying to show you guys that the units are Pascals, because they are gauge pressure units. Okay, Mark. Stretch it. Anybody got a number for me? Star?
2011 050.
No decimal anywhere? Okay, now remember, if I want to find the overall pressure or the absolute pressure, okay, I have to just add that PO, that absolute P naught, very good, P naught, the absolute pressure there, okay? I need to add that on.
What is that value? What's right there?
So again, to get absolute, I take my atmospheric pressure and I add rho GH. Well, I already figured out rho GH. It's right here. I know absolute pressure. That's given. So if I want to add this though, what do I need? Because I need what? I need the same units. So write this, please, as the following. Please write it like that instead. Because again, this number is 101.3 kPa. If I want to add to kilopascal, I need to add kilopascal. So even though this is what I got from my gauge pressure, I should rewrite it like this, so that I can then place it here, so I can add it with P naught. P naught is units of kPa. If I want to add kPa to kPa, I have to actually change it. So this number converted to go to kilo just means move it back 3 spots. So I moved it 3 spots, and there's my decimal.
So what about the 0.05?
You can write it, but I'm going to show you that it doesn't really, I mean, the number's not that significant, but yes, we should write that. I mean, it's just going to add on at the end. There's going to be a 3, and now there's a 5 at the very end. That's all it's going to do. But take a look, people. Even at 200 meters, this does have a good emphasis on the problem. This was only 2,000 as an answer. This is 100. So if you ignore this, that's a pretty big portion. You're talking 1 out of 20 right now. It'd be like saying to yourself, oh, last year I grew 6 inches. But that's not a big deal, so I'm just going to never consider that my height. That wouldn't make sense, right? Because 6 inches in your height is a pretty good amount. This is a pretty good amount relative to this. We want to think of relative magnitudes. This is where, you know, critical thinking comes into play. So we got 2112.35 kPa. And again, for these problems, we're going to leave stuff in kPa. Kilopascal is the accepted unit, is the most widely used unit. So please keep it that way. If you're working on your car, you'll notice that units are PSI, which is pounds per square inch. That's fine. Good to know also, and it is good to know that if you're ever filling up your car, if you want to write this down, most cars take between 31 and 33 PSI as their pressure for their tires. And you know how you can figure that out? Open your driver door. On the inside of yours, once you open the door, look at the actual door panel. On the inside of it, look down at the bottom, you'll see a little sticker there. It's got a bunch of like numbers and stuff. And you'll see tire pressure. And it'll tell you in the winter another time usually. And it'll tell you they're usually 31 to 33 in that range. Some tires take 34 or 35. But generally speaking, if you don't know what it is and you get to 32, that's a good safe bet. If you're below 31, usually low. Above 33, usually high on pressure. And either of those can cause flats. Low air and high air causes flats, by the way. If you have high air, you get what's called a blowout, where the tire will actually split. Okay? So if you like hit a really sharp edge, the tire will split because there's too much pressure. If it's under pressure, the tire will puncture. Okay? The tire will easily puncture, which is where you get like you run over like a tire and it punctures into your tire. Okay? And then
Run over
run over a nail. Thank you.
That's what happened one time with my mom for you. Like you rolled over a nail, right? But it's just stuck in it.
And did the car still go?
Yeah.
I know. Is that crazy? Now, eventually though, it does leak air. Guys, if you run over a nail, you can technically still drive your car, provided it doesn't lose enough air. But you have to get it changed because air will eventually seep out. Anybody know how to fix a plug on a tire?
No, they just
You guys know it?
Don't you have to, like, to know where the good
Yeah.
Don't you have to put some water?
Yes.
And put a blue thing in
Awesome. So that's the trick, guys. If you ever think you have a flat, you take your tire off, you take like a kiddie-sized pool, fill it up with water, put the tire underwater. Wherever you see air start bubbling, that's where the leak is. Because remember, when there's a leak in your tire, isn't air escaping? So if you put it underwater, you're going to see the air bubbles coming out.
So remember,
Whenever there's a leak.
carry a kiddie pool in your car.
Well, here's the thing. Here's the thing. You can't do that if you're on the road. But at like a,
You can. Jump to the lake.
at a mechanic, you know what they do is this. They run like a fluid over it, and they see where it starts to bubble. And then, the way they seal them, you know what I do?
My dad told me yesterday.
Go ahead.
No, because like I was at home and I asked my dad because he had like a tool which was like a cork, and I was asking what it was. So what they do is that they get like this tool which has like a gigantic handle and it looks like a cork needle, and they plug it, they put it into the tire where the hole is, and they like make the hole bigger to clean it up around it, and then they get these plugs which have an adhesive around it, and then they have another tool which is exactly the same way but it has a hook inside. And they push it inside of the bigger hole and they pull it out, and the hook and the adhesive which was on the hook would stay in there and the pressure would squeeze it.
And the other last thing to add, it's a plug. So everybody always worries what if it pops out? It eventually melts and becomes one with the tire. It's the same material. It's not the adhesive is something that sticks to these together. This is more of a fusion.
Isn't it like a car?
Guys, I put up some things if you want to look tonight. I write it on the board right now so you can look at the video, but it's up there already. Just to read and look at 2 examples on 283, please.
Yeah, random fun fact history.
You gonna see the hill, you gonna see the red.
Anybody looking thin like the other thing.
Hey, she can get it too.